The present video is on the fourth subtopic of digital circuits, and it's combinational circuits. Before we start our presentation, we'll summarize the video contents here. The digital circuits have been classified as combinational circuits and sequential circuits. Combinational circuits have no memory element, while the sequential circuits have memory, that is, they have the feedback path from the output to the input. Combinational circuits have the following class of circuits, that is arithmetic and logic functions. Second is data transmission type, and the third one is the code conversion type of circuits. Present video is on the circuit based on arithmetic logic functions, and such circuits are like adders, subtractors, multipliers, comparators, etc. A brief overview of adders, subtractors is given, giving points which could be helpful in problem solving. Different adders types are indicated with their advantages and disadvantages. A 2-bit by 2-bit parallel multiplier circuit is illustrated to bring about the hardware needed for the circuit. AND and multiply truth table are identical, so product term generated by AND and sum using adder or XOR gate. The last topic is on magnitude comparator. 1-bit magnitude comparator is illustrated and through truth table and the logic diagram, and the same could be extended for more than 1 bit, that means 2 bits, 4-bit comparators, etc. So we would start the video presentation. Here we'll see here, this is combinational circuit, and this is on digital circuits part 4, and this is part 1 of combinational circuits. Digital circuits are classified as either they are said to be a combinational circuit where the output depends on the present inputs at that instant of time. So this is a corresponding block diagram here, and we notice here these are the n inputs connected at the input side and m output variables on the output side, and the output here depends upon the present inputs at that instant of time. So just such a circuit is a combinational circuit, and gates are very good examples for the combinational circuit. There are many more circuits which come under the category of combinational circuits. Similar to the sequential circuits here, the here output depends on the present input and also on the past outputs. That means output is here, we notice here the output is fed back to the input. They are like inputs, the outputs, and the output is fed back here to the input side. There could be more than one feedback path here, not only one. So such a circuit, this whole circuit along with this memory element, this forms the sequential circuit. Okay. Now part 1 here discusses the arithmetic circuits such as adders, subtractors, and comparators. Basically it's arithmetics and logic circuits. Adders, subtractors, multipliers, they come under the category of arithmetic circuits and comparators under the logic circuits. Part 2 will consist of other combinational circuits such as decoders, encoders, multiplexer, demultiplexers, etc. Now we'll start with the arithmetic circuits. We know that computer consists of arithmetic circuits that can add, subtract, multiply, divide binary numbers, because computers use binary numbers. So basic unit of arithmetic circuit is the adder. Adder is one of the basic unit of the arithmetic circuit. Now we'll see about the adders, then subtractors, and so on. Now we notice here this is a circuit for not circuit, this is a half adder. Adds two binary digits and produces sum and carry, and it's a half due to lack of input carry. That means there are only two inputs bits. The carry bit is not added, but at the output you get sum and the carry also. Full adder adds 3 bits and produces sum and carry. It produces sum and carry, but it adds 3 bits. That means carry bit is also added in this, so that's why it's said to be a full adder, or a full adder is said due to because the carry bit is also added here. Now, as an illustration, we have taken an example here for an half adder circuit. This is the half adder circuit. We have shown here the truth table for the half adder. Here inputs are A and B, and sum and carry are the outputs. So we can see this truth table. When we add up 0 plus 0 is 0, that means sum is 0 and the carry is 0. 0 plus 1 is output is 1, sum is 1 and the carry is 0. 1 plus 0 is same as 1, sum, and there is no carry. But when we add 1 plus 1, out sum is 0 but the carry is generated. So this is the corresponding truth table. From the truth table, from the column of sum, you can find out the expression for the logic function and or a Boolean expression. So this corresponding to 1 you can write here this A bar B and this A B bar, and this is A exclusive B, and C similarly from here for this output carry to be 1 you can find out the C equals to A and B. Okay, so minimum number of NAND gates or NOR gates needed for half adder are 5. You can find out this a very simple I would say an example that you could work out. Now we see the adders and subtractors. The adders and subtractors we'll try to compare together and try to see how these adders and subtractors would help us in giving the solution to some gate problems. So we are writing here the logical equations in the table, and key points are highlighted here. This is for half adder. The sum is A exclusive of B. The difference here A exclusive of B, both are same. And carry out here is A and B. This borrow out here is A bar B. There is a difference here. The A is barred here. And these terms here are well-known terms like sum, difference, C in, C out, and so on. If you see the full adder circuit, sum is A exclusive of B exclusive of C in, and difference here A exclusive of B exclusive of B in. So only difference here carry is a borrow, and C out similarly you can write the expression for C out and B out, and they could be rewritten in this form. So later we'll see, try to compare these expressions and try to find that when a circuit is adder and when it is subtractor, only by seeing these expressions here. So these are some of the points here which are brought out. Half adder subtractors are implemented using a XOR gate for sum and AND gate for carry and the borrow. That we have already seen. Full adder, subtractors, sum and difference implemented using 3 input XOR gates. C out and B out expressions are the same except input variables. They are the same except the input variables. Here again, except the input variable A is complemented here. If you see if we try to see here the expression for carry here, this is A or B, A plus B, C in plus A, B. In a subtractor circuit, this input, this is complemented here. This is the only difference, otherwise both the expressions are the same. So that's why I say using 3 input XOR gates and C out and but B out expressions are the same except input variable A is complemented. N-bit adder requires n minus 1 full adders and 1 half adder, because there is no carry generated with the LSB, so that's half adder would do the job. Now here we have given here adders and subtractors continued. Some more key points like full adder implemented using 2 half adders. That means by using 2 half adders you can implement the full adder. An n-bit adder can be built by cascading n full adders. That means if there are n full adders, you can cascade them to increase the number of bits. Full adders can be converted to full subtractors by complementing input A prior to its application to gates that form the carry output. So many times the circuit is formed which is combination of both adder and subtractor circuit. So there you can do the same here. That means you can use a corresponding logic circuitry so that the input variable is complemented in one case, other it is not. That means when it is adder it is not complemented, when it is subtracted it is complemented. Now parallel adders, this is a diagram here. You just see here this parallel adder here, this LSB least significant bit, this carry in is counted. There is no carry generated because this is the first LSB. These are two inputs A0, B0. There is a carry output is C1 here, then C1 is fed back to the next significant digit, C1, then C2 to C3, this carry in and this carry out, and these are corresponding inputs to these. So this is a 4-bit binary parallel adder. This IC indicated here, IC 7483, is a 4-bit full adder. Speed is limited due to carry propagation delay. That means we notice here the carry generated here will propagate to next bit. Similarly, this carry generated here will propagate to next bit. So it will take time here. That is said to be a carry propagation delay. 4-bit adder output is generated after 4 times of propagation delay. If delay is about say 50 nanoseconds typical, then 4 TP will make you 200 nanoseconds. So this 200 nanoseconds is really higher for fast computers, because the computers have to do fast calculations, and if the adders arithmetic circuits are slow, they will not be able to do faster operations. Now the process used here is a look adder carry addition. Extra hardware is used so that it finds whether the carry would be generated or not, and accordingly it will be taken care of. And such circuits are called as fast adders because they don't have the propagation delay. Now another kind of circuit is a BCD adder. A BCD adder adds 2 BCD digits and produces some digit which is also a BCD. So this following steps are there. Add 2 BCD numbers using binary addition procedure. If the 4-bit sum is less than 9, sum is in the BCD form. We don't have to worry about it. If it is greater than 9 or the carry is generated, the sum is not in BCD form, then to be converted to BCD form. And then we add a digit 6 decimal. This is 6 decimal or 0110 should be added to the sum to produce BCD results. And then the serial ladder addition performed by bit is simpler. Circuitry and but the speed would be lower. In the case of serial ladder, you can perform the addition bit by bit, but the speed would be slower as compared to parallel ladders. Now binary multipliers. Approaches which are used are the shift methods or the parallel multiplier or the array multiplier, but the speeds increase considerably in a parallel multipliers at the cost of increased hardware, although the hardware cost would be more. So this example which we are taking here is a 2-bit multiplier. It's a parallel multiplier. As an example, this is LSB, this MSB is a 2-bit by 2-bit multiplication. So the A0 A1, B0 B1, this is a multiplicand multiplier, and B0 corresponding partial product. These are the A's. Multiply B0 A0 and B0 A1, A1 B0. So similarly you can make the second partial product and add up together. These are the output O0, O1, O2, O3. What we notice here in this circuit or in this multiplier, what we observe here, this O0 is A0 B0, O1 is A1 B0 plus A0 B1, C0 is the carry generated by the previous bit. Similarly, this is a carry of the previous bit, this carry of the previous bit. So if we observe here, if we try to see the truth table of a multiplier and the truth table of a AND gate, they are similar. So you can use the AND gate to get these multiplication products, and so we can get the products generated through the AND gates and addition to be done by the adders or maybe XOR gates. Now this is the corresponding last topic here in this part 1. These are magnitude comparators. These magnitude comparators compare the magnitude of two numbers A and B, and they'll generate one of the following outputs, like whether A equals to B, A less than B, or A greater than B. So the numbers are A and B here. We have taken magnitude comparator, which is 1-bit magnitude comparator. This is the corresponding block diagram for magnitude comparator here, A and B, A greater than B, equals to B, less than B. Now we can notice here for A equal to B, this is an XNOR gate. If you see the corresponding truth table for the 1-bit comparator, you will notice this corresponds to the XNOR gate. That means the two inputs are same, you will get output 1. Similarly, A is equal to B, you will get an AND gate, and this corresponding B is also an AND gate, and this circuit is being implemented here. A equals to B, greater than B, A less than B. This is the corresponding logic circuit here that you could make through this. Some principle is extended for n-bit magnitude comparators. It means same principle could be extended for higher number of bits. We have taken here for 1 bit, we can take for 2 bits and more. IC 7485 is a 4-bit comparator, and you can use address decoding. This is used for these comparators, address decoding in computers and for the control application. These have been some of the applications for comparators. What we notice here, these comparator circuits, when compare 2 bits, 2 by 2 bit comparator or 4 bit by 4 bit comparator, normally the circuits are the corresponding truth table is very unwieldy. So writing the corresponding truth table, you have to be more careful when it is for 2 bits or 4 bits. Later we'll take up an example in video solution. There we'll take an 2 bit by 2 bit comparator circuit, and there we'll try to give the corresponding truth table, and we'll see how we work out with that truth table to get the results for the comparator circuits. So this is all for this part 1 of this combinational circuits, and we'll see in part 2 the remaining combinational circuits like multiplexer, demultiplexers, decoders, encoders, and many more circuits. We'll try to see those circuits. Thank you.